All right, week 9, problem 13. A series circuit consists of 3 identical lamps connected to a battery as shown in the figure below. The switch S, originally open, is closed. What then happens to the brightness of lamp A? All right, so even though I read it, I wasn't actually listening. So, switch S, originally open, check, then we close switch. Okay, so what happens to the brightness of lamp B? Okay, so let's see. I'm gonna say each lamp is resistance R. So current equals, so the brightness is going to be proportional to power. So is I squared R. So you're going to do brightness something proportional. I should make a proportional sign. Yeah, whatever. You get the idea. So I, which is current, is going to be V divided by R. So the total current coming out of the battery will be epsilon. Therefore, current total equals epsilon over 3R. Okay. So then after we close the switch, we're going to have, I'm going to call this initial and call this final. It's going to be epsilon over 2R. So the idea here is originally we had 3 batteries, 3 light bulbs in series. So current then had to go through each of them. So in series, just add them together. 1, 2, 3. Got it. So then the current is going to change because then we're going to have more current. So now we're going to have less resistance because we have basically only 2/3 of the lamp, so we're going to have less resistance. There's going to be more current drawn. And so what's going to happen is, I don't know what the total brightness is going to be, but for this guy, we're going to have I squared R for the brightness. And if I goes up, then the brightness is going to go up. And the resistance for the individual lamp is going to stay the same. So raise, or increase, or go up. Brightness of lamp B. What happens to the brightness of lamp C? It's going to goes to 0. So lower 0, whatever. Because the idea here then is current is going to take the path of least resistance. If the least resistance is 0, then all the current is going to take the path of 0. So, yeah, path of 0. What happens to the current in the battery? So this asks about total current, which is kind of what we already addressed here. So the current from the battery, the current total, initially it was epsilon over 3R. Then once we close the switch, it only goes through 2 resistors, or 2 lamps. And so it's going to have less resistance, so we're going to have more flow. We're going to have, if you think of it hydraulic analogy, you have 3 filters in a row. If you take out one of the filters, you're going to have less resistance to flow. So there's going to be more flow. You're going to have more flow from the battery. Yeah, you're going to have more flow from the battery because you have less resistance to that flow. So this guy, bam, goes up. So the current from the battery rises. What happens to the potential difference across lamp A? Okay, so initially we're going to have, so voltage initial, there's going to be a voltage drop across, so we have 3 batteries, or three lamps. And the voltage drop across each lamp, because they're identical, has to be the same. So we're going to have the total voltage we have, which is epsilon, and it's going to drop 1/3 of its voltage across each of them. So then, make an arrow there so it's not actually really equals, it just implies. Then after we close the switch, we're only going to have 2 lamps, which is going to be epsilon. So it's going to drop half the voltage across each lamp. So what happens to the potential difference across lamp A? So the potential difference will rise. And that kind of makes sense too. If you're going to have, so A and B are going to be the exact same here. So if we're going to have more current across A and more current across B, to get more current for the same amount of resistance, then what we're going to have is a greater potential difference across it. So if you want to get more flow through a pipe, you need to have to lower the resistance of the pipe. But if the pipe stays, same resistance, same filters, whatever, then you're going to have more pressure across each side to cause that more flow. That more pressure is the potential difference. So the potential difference across A will rise. What happens to the potential difference across C? All right. So before initially we're going to have epsilon over 3. 1/3 of the total voltage drop is going to happen across C because they're the same. But after we close it, current's going to go this way. And since these parts, this side and this side across the lamp C is connected by a wire with the 0 resistance. Therefore, there's going to be 0 potential difference across C. So the change goes to 0. There's going to be 0 resistance across C. There will actually, or potential difference across C. There'll actually be some because the wires have some resistance, but we're going to ignore that. Pretend 0, ideal. What happens to the total power delivered to the lamps by the battery? All right. I'm not quite sure of this one, so I'm just going to do it this way. So power equals I squared R. We know what the initial current is, and we know what the initial rate R's are. So we're going to do, this is a current, so I'm going to do epsilon over 3R, which is I. We're going to square it, I squared times R. And then we're going to multiply it by 3, since we have 3 lamps initially. So if we look at this, we're going to have epsilon squared over 9R squared times 3R is epsilon squared over 3R. So it makes sense because V power, another way to write power is V squared over R. We got V squared over R. Okay, that seems reasonable. That'll be the total power distributed, where R is just one of the resistors. Also makes sense too because each R is the same, so 3R is just the equivalent resistor. Yeah, that seems reasonable. I would totally believe that. Totally believe it. All right. I think we're probably going to get some sort of similar thing going on here. So I'm going to do P equal power equals I squared R, which will give us epsilon over 2R squared. This is the power to 1. This is the current squared. And we multiply by the resistor, and we're going to have 2 lamps in the second scenario. Okay, so we multiply this out. We have epsilon squared. Nope, that's not supposed to be a 9. 4R squared times 2R. Simplify this, we have epsilon squared over 2R. Okay? And so this is going to be a smaller than that. Bam, okay. So, originally closed. What happens to the total power delivered to the lamps by the battery? So the power delivered by the battery rises. Power delivered by the battery rises. There's actually more power, joules per second, coming out of the battery when you take off one of the lamps, when you bypass one of the lamps. Now this makes sense because the phrase short circuits like basically means you bypass a lot of the resistors. They cause fires, and things get hot because of I squared R losses. So when things get hot, it means they're putting a lot of power out into it. So it makes sense that this is short circuit, i.e. it's taking a shorter path than it was intended. That's going to create more heat. You know, like kind of if you ever carry like batteries in your pocket with some pocket change, quarter or nickel, something slides up against the battery, something connects, and all of a sudden your pants on fire. It's not actually on fire usually, but it gets hot and uncomfortable, and it surprises you because you don't expect your you don't expect your pockets to be uncomfortably warm. Okay, so what happens to the total power delivered by battery? Total power rises. And I showed it doing this way. I like to do it that way just because there's minimal ambiguity. The smaller, more certain steps you can take to get an answer, I think the better. All right? So this is a pretty sure review question, but it's pretty good to understand how each of this works. All right? Perfect. See you on problem 14.